All right. So our goal for today is to get through numbers 5, 6, 7, and 8. Okay, and then, and 9 and 10, I think, as well. I believe so. Yes, we want to get through all those, okay? So we got to get rolling here to get through all those different questions, okay? We're going to save the last few questions, which are going to be 1, 2, 3. Okay, they kind of restart the numbering. 4, 5, and 6. Those are kind of like more AP, or from an AP kind of practice. So we'll look at those, tomorrow. Okay, so we're just going to jump right in here. Remember that yesterday, right, we learned about how to do related rates. We have these kind of like guidelines for us to use when it comes to related rates. The problems you did for homework were already kind of like nicely set up for you and nicely done, so there wasn't as much preparation necessary. You kind of like could just do the derivative and then start plugging stuff in. But today's problems and then tomorrow's problems will involve a little bit more preparation work, a little more figuring out what formula should I use, how can I relate these variables, and then of course plugging stuff in. So just to refresh our memory here, the first thing we want to do when we come across these related rate problems is to identify all of the given quantities and the quantities to be determined. We want to make a sketch and label that, and that can be helpful. Okay. Number 2, we're going to write an equation that relates those quantities. Normally, it's going to be a geometric equation. Okay, it's going to involve geometry. Again, you are responsible for area formulas. You're responsible for perimeter. Okay. You are not responsible for surface area of three-dimensional objects or for volume formulas. Okay. So don't fret if you don't know those, but you definitely need to know. The area of a square is, side squared, or the area of a circle is pi r squared. And the circumference of a circle is 2 pi r, or pi d. You need to know those for sure. Number 3 then, once we've got that relationship between the variables, we're then going to take the derivative to then relate the rates of those variables, the rates of change. Okay, relate the rates. And so that's always with respect to time t, because we're measuring things with respect to time here. And then finally, step 4, after you've taken the derivative, you're going to plug in values. Plug in your known values, okay? You're going to plug in your known values. And then, of course, solve for the required rate of change. And, of course, we want to make sure that we are giving correct units there. All right? So, just to refresh our memory. So now let's go here to example 5. And we're talking about liquid dripping into a conical cup. Right? So you can think of like one of those cups at the water cooler or whatever. Those are conical cups, right? And so if we draw a little picture here, right? We've got like a conical cup, like so. All right, and forgive me, I'm not the greatest artist here, but look at the idea, right? And we got water kind of dripping in. Okay, like that, and that's going in at a rate of 2.5 cubic inches per minute. Okay, and then we've got some water already in there as well. Okay, we're told the cup has a height that is always twice the radius. All right, so that's going to be probably something we're going to need to use there. And we want to know how fast is the liquid level rising in the cup when the liquid is 2 inches deep. Okay, so talking again, this is similar to that problem we had for the homework there. Talking about the depth of the liquid in the cup, right, is the same thing as talking about the height of the liquid in the cup too. Okay, so depth and height, same idea. Okay, so let's, I guess, figure out some things here. So 2.5 cubic inches per minute, liquid is dripping into a conical cup at the rate of 2.5 cubic inches per minute. So that value there, what can we describe that as? dV dt. Is right, yes, it would be dV dt. Okay, it's the rate of change of the volume with respect to time. All right. If you're like uncertain about that and you want maybe a way to kind of help confirm it for you, you can also look to the units, right? We're talking cubic inches per minute. So the per minute there, that means it's going to be a rate of change, and it's cubic inches. Well, what do we measure cubic inch? What measures cubic inches, or what does cubic inches measure? Volumes, right? Volumes. And so it's going to be 2.5 there. Okay. Are there any other values given to us here? Aha, bless you. How fast is liquid level rising in the cup when the liquid is 2 inches deep? So this will say is like 2 inches. I can label that on my picture too. Okay, oops, I'm off the screen there. There we go. Okay, so right, so then we would describe that as maybe H equals 2 inches. Okay. And what quantity are we trying to determine here? What's the question that we're being asked? So dH dt, how fast is the liquid level rising? So it's the rate of change of the level of the liquid. So we want to find dH over dt. What is that? That's what we're trying to find here. Okay? That's what we're trying to find, dH dt. How fast is the liquid level rising? That is our question. Okay? So, what would be a good formula to use here to relate these things? What could we use to represent this scenario, what situation? Yeah, Shuttle? Volume of a cone, that's right. Will you need to memorize that? No. Now, it's not given in the problem here, but it would be given to you. So, yes, we're going to use the volume formula for a cone. If you don't forget, it is volume equals 1/3 pi r squared h. Okay, you might see different ways. Some people might write like pi over 3 r squared h, whatever. Okay, it's 1/3 of the cylinder formula.
Don't we also know the radius?
Okay, so what do we know about the radius?
It's half.
Okay, so the radius is half the height. So yes, let me write that in the way it's written here, and then we'll discuss that. So it says here the cup has a height that equals twice the radius. So we also have this relationship too. H equals 2r. Okay, H equals 2r. All right, and I'll show you how we're going to use that in just a second. Okay, now, what are we trying to find in this problem? dH dt, right? And what we're trying to solve here, we want to solve for dH dt. If we go to our volume formula, we've got our volume formula here. Okay, so we have our equation, right? And so that's like our step 2, write an equation, usually geometric, involving the variables that are given or are to be determined. And then step 3 says to use the chain rule, we're supposed to then differentiate. Okay, now, if I go to differentiate my formula here, what rule are we going to have to use to take the derivative of that? Product rule, because we've got r squared times h. Now, we're not going to do that right now. Just let's pause. If I go and take the derivative of this, as it's currently written, I'm going to have dH dt, h's, but I'm also going to have r's and dr dt show up in there. Okay? And that's going to be a problem, because I have no idea what dr dt is. We have no idea about the rate of change of the radius. We're not told anything about how the radius is changing, what the rate of change of the radius is. We could figure out the radius itself. Because we have this relationship right here. The height is twice the radius. So at the instant when the height is 2, we'll know the radius will be 1, for example. And that'll be helpful there. But we don't have a way to kind of like come up with, well, we really don't want the radius in our problem right now, because all we're interested in is dH dt. So what we can do is rewrite our formula here in terms of, well, what variable should I rewrite this in terms of? H's, because I just want to find dH dt. So I'm going to rewrite this using this relationship, okay? Now, obviously, in different problems, we're going to potentially have different relationships, right? Here, specifically, we have that the height is always twice the radius. In other problems, it might be a different kind of relationship. You'll need to change, what is being plugged in. But in this case, we know that h is equal to twice the radius, which in other words, as Lander said, that is then the radius is equal to the height divided by 2. Okay? And so where we have r here in our equation, we'll rewrite that 1/3 pi times h over 2 quantity squared times h. Okay? And again, we are rewriting this. Rewrite in terms of h because we want dH dt. Okay? Rewrite it in terms of h because we want dh dt. That's the idea there. All right. Now, should we take the derivative right now, or should we maybe do something else? Yeah, simplify it. So let's simplify this first, because right now it's kind of a bit of a mess. All right, so we're going to have h squared over 4 times h, which we can then combine together. So h squared over 4 is the same thing as 1/4 h squared. I'll multiply the 1/4 with the 1/3 and make it 1/12 pi, and then h to the third. 1/12 pi h to the third. We all okay with that right there, yeah? Okay. And so now finally, what can we do? Take the derivative with respect to t. So derivative of v with respect to t, dv dt. The derivative of, 1/12 pi, that's just a coefficient, so we'll bring the 3 out front. 3 times 1/12 is going to give us 1/4 pi h squared times dh dt by the chain rule there, okay? And now we've rewritten everything. So now we can finally substitute stuff in, right? What can we plug in for dv dt? 2.5. What can we plug in for h? The 2. And then dh dt, that's what we're solving for. So we'll leave that be. Okay. 2 squared, 4 times 1/4, 1. So all we have over here on the right-hand side is a pi. We'll divide pi over, and so dh dt is 2.5 over pi. And what would our units be here? Inches per minute. Exactly right. Again, if you're unsure, right, just think we're talking about the rate of change of the height. So the height would be in inches, but the rate of change of the height would be then inches per minute. Height per time. Inches per minute, okay, right there. And so 2.5 over pi inches per minute. Here's our answer there. Okay, questions on that? Typically, if your volume formula involves more than one variable, you'll have some sort of relationship between those two variables that will allow you to then substitute in so you can get your volume formula in terms of a single variable. Okay? Typically that will be the case. So here we had the volume was in terms of r, radius, and height, okay? But we had a relationship given to us that allows us to then rewrite it in terms of the variable whose derivative we wanted, right? dh dt. Typically that would be the case. All right? All right. Let's try the next one here. Number 6. A television camera at ground level is filming the liftoff of a space shuttle that is rising according to the position equation s equals 50t squared, where s is in feet and t is in seconds. The camera is 2,000 feet from the launch. Find the rate of change in the angle of elevation of the camera 10 seconds after liftoff, right? So the idea is that the camera is not just like stationary. It's going to be moving with the rocket shuttle, so it's always like kind of in the center of the frame, right? The camera will be rising as the rocket's kind of blasting off, okay? So it's not going to just be a stationary shot. It's going to keep, it's going to be locked onto the rocket, we'll say, so to speak. All right, so let's draw a picture of this. All right, so we've got the ground. All right, we'll have our camera. I'm going to draw the camera over here to the left. Okay, there's my little camera. All right, and then we've got our rocket ship. Oh, goodness. I guess it should be going straight up in the air, not like crooked like mine's going there. There we go. Okay. Okay, a little rocket ship, USA. All right, so there we go. Okay, I guess I should give it some flames and stuff too, because that's what they do. All right. And so the camera is filming the rocket shuttle there, or the space shuttle, I should say, space shuttle. Okay. The space shuttle is rising according to, so there's our situation, I guess we'll say, right? We're assuming it's taking off perpendicular to the ground there. So let's label some things again. So we're told that the space shuttle is rising according to the position equation, s equals 50t squared. So the height, its position off the ground will be s equals 50 times t squared. Okay, the camera is 2,000 feet from the launch. So here was the launch, so 2,000 feet. Bless you. Okay, right there, 2,000 feet from the camera, or from the launch site. And it says to find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. Okay. So. What is the variable that we're trying to find here? Or what can we name that variable for the rate of change in the angle of elevation? How will we name that? dA over dt? We could use that. Absolutely. Typically, what do we use to represent an angle? Theta, right? So maybe we should use d theta dt. But dA dt is not wrong. You could absolutely use an a there if you wanted to. So let's say d theta dt. That's what we're trying to solve for here. Okay. Where is theta going to be located here in our diagram? Down by the camera, right? The angle of elevation. Remember that an angle of elevation is always from the horizontal looking up. Okay, so from your observer, from the horizontal of the observer here is the camera, the horizontal of the observer looking up, right? That's an angle of elevation. So there's theta right there. Okay. So, what can we use here? Okay, what can we use here to relate these things together? What can we use? Yeah, Michelle. Tangent. Yes. How did you know that we're going to use tangent? Opposite over adjacent. Exactly right. Exactly right. Okay. So we're going to say that, bless you, the tangent of theta. Okay, there we go. Tangent of theta is going to equal what over what? Okay, so S over the 2,000 there. Yep, if we want to do it that way. Okay. Okay. The height of the rocket, which is changing, right, over that 2,000 there. Okay. So then, we've got our equation that relates our variables together here. How should we proceed? So, nope, we don't want to do inverse tangent. When we have the equation that relates everything, and now we want to relate the rates, we can take the derivative. We want to take the derivative at this point, right? Once you have your equation, right, that's a step, this is again step 2, we wrote an equation, usually geometric, so trigonometric in this case, involving the variables that are given or to be determined. Using the chain rule, implicitly differentiate both sides of the equation with respect to time t. So we're going to take the derivative here. Okay. So tangent of theta, what's the derivative of tangent? Secant squared theta times, remember we're differentiating with respect to t, so the derivative of tangent is secant squared theta times d theta dt. Yep, don't forget that implicit differentiation we're doing here because it's always with respect to time. Equals, okay, now remember, s over 2,000 is the same thing as 1 2,000 times s, and so then what's the derivative of s with respect to t? 1 2,000th ds dt if we want to. Yep. Okay, because 1 2,000th is just a coefficient. ds dt is the derivative of s with respect to t. Okay. So, we weren't given a whole lot of information here that we can plug in. I mean, for example, we need to come up with a theta, right? We're not told an angle here in this problem, but we need to come up with a theta because we're trying to solve for d theta dt. So every other variable, theta and ds dt, we need to come up for a value for that. So, well, let's hold off on the theta for right now, maybe. Let's look at the ds dt. How can we find ds dt here? Take the derivative of s, right? So, Sean, what is ds dt going to be? 100t. Yeah. If s is 50t squared, then ds dt, the derivative of s with respect to t, will be 100t. No dt dt, right? Because we're taking the derivative of something in terms of t there. Okay? All right, so that's an expression. That's an expression, so we could put that in here. So I could say, secant squared of theta times d theta over dt equals 1/2000. Now, instead of the ds dt, we can put a 100t in there. That's helpful. But what else do we know? What do we know about t? T is what? 10 seconds. Find the rate of change in the angle of elevation of the camera, 10 seconds. There's our t. So t equals 10 seconds. Okay, that's our time. So we'll plug in 10 there for the t. And so we get 1/2000 times 100 times 10. Okay, which is 1,000. And so that's simplified to 1/2 here. Okay. We still need to come up with a theta, though. Still need to come up with a theta. Okay. Originally, Shelby told us that the tangent of theta relates the opposite over the adjacent, like that. How can we then use this to come up with what theta has to be? Plug in what for t? 10, exactly right. 10 because we want to know the rate of change of the angle of elevation of the camera 10 seconds after liftoff. So with this relationship, we can plug the 10 in here. So we'll have tangent of theta equals 50 times 10 squared over 2,000. Okay. So 10 squared is 100 times 50 is 5,000. 5,000 divided by 2,000 will be 5/2. Okay. And then, how should we proceed from here? Inverse tangent, which means we need to use what? Calculators. This would be a calculator active problem, okay? You wouldn't be able to do this otherwise, all right? So, theta is going to be tangent inverse of 5/2. Okay, tangent inverse of 5/2. Now, here is a very good question. I'm not sure whether we should do this in degrees or in radians. I think you would have the freedom to do it either way. You would just need to watch your units then when you describe it at the end. So if your calculator's in radian mode and you want to do it in radians, that's fine. I'm going to do this in degrees though, because to me, in the context of the situation, degrees would be kind of the way to go. Yes, radians when we're kind of like in an abstract setting with like trigonometry and stuff like that, but in a situation like this, I feel like degrees is the more typical kind of way to go. So we'll do it in degrees here just because, okay? But I think it would be okay to do it in radians and then just make sure your answer is in radians too. So in degrees, I get about 68.199 if I round, okay? Okay, degrees there. So about 68.199. So that is our theta at the instant of 10 seconds. So we're going to plug that in now for secant squared theta. Okay. Plug that in for our theta. And now we have everything that we need, right? So we're going to go ahead and calculate what secant squared of 68.199 is. Okay, so now to do secant squared, there is no secant squared button on our calculator. So how can you do secant on your calculator? There's no button, but how can we do secant? 1 over cosine, 68.199. We can hit enter if we want to, and then just make sure you then square that solution. And so there is secant squared of 68.199. Okay, about 7.250, we'll say. Okay, just like that. And then we'll divide that over 1 over about 14.500. Okay, and that would be what units? Degrees per second. Okay, yes, degrees per second. Degrees per second. Okay. So, question? Okay, so how did you try to do it differently?
I divided by secant squared, and I got 1/2 cosine squared of x, and I had to do out front.
Okay, so sorry, so one second. So you had the secant squared over here, and you made it, so you had a 1/2 cosine squared, you said, okay? And so that left, so you had d theta dt equals 1/2 cosine squared.
And then I brought the 2 in front to make it cosine theta. Can you do that?
So we can only do that. So that what you just did right there, that would be like if we were taking the derivative, the 2 would then go out front, like by the chain rule and stuff like that. But with the cosine squared by itself, there's no property of cosine that allows something to 2 out front.
Okay,
So.
thank you.
So what you did right here, perfect. You could absolutely just sub in from here then and go from there too. So, all right, question.
If you did the arctan at the beginning and plugged in the equation for S, and it was a lot less steps.
Okay, so show me what. So you did. So you started back here at the beginning.
Yeah.
Okay.
And I just did the arctan on both sides.
Okay, so let me see here. I'm going to run out of space. I'll try and squeeze it in over here. Okay. Okay, so starting with our original formula here, and I'll start at the top and maybe skip around that other piece. So equals S over 2,000. You said you did inverse tangent of both sides. So we have arctan of S over 2,000. Okay, and then you said you took the derivative from this point.
Well, I put the 50t squared in for S.
Put the 50t squared in. Very good. That's fine. So then we'll plug in the 50t squared, but then we'll simplify it too. So let's see here, 2,000, and then the 50 simplifies to, oh goodness. So we could have. So we'll actually, we'll leave it. We'll leave it. If that's what you did, we'll leave it. So 50t squared over 2,000 like that. Okay, just like so.
Yeah. And then
Okay.
I just took the derivative.
Took the derivative from here. So this is possible, right? We know the derivative of arctangent. All right, so then it will be d theta dt equals 1 over, our u here is this whole quantity, so it's 1 over 1 plus 50t squared over 2,000 squared. Okay, then times the derivative of what was inside that by the chain rule. So that would be, and again, the 50 and the 2,000, they're just a coefficient, so really just the 2 will go out front, so it's going to be like 100 over 2,000 t to the 1. I think I did that right. Looks good. Okay, so you said that's what you did, and then times, well, dt, which is just going to be simplified out. So.
And then you just plug in 10 for t.
Aha. So this one is all in terms of t here. Okay, and we're just going to plug in then the 10. Yeah, so d theta dt equals 1 over 1 plus 50, and I guess I'll just put in the 10 here, over 2,000 squared times, oh, sorry, thank you, 10 squared too. And then times 10. Okay? So we got to be careful how we type this in our calculator here. So I'll probably take this little piece right in here first. So 50 times 10 squared divided by 2,000. So 2.5 plus 1. So 3.5. So 1. Oh, I forgot to square. Sorry. So 2.5 squared plus 1. So 7.25. 1 over that. Okay. Times. So that decimal right there is this right here that we did. And then times 100 over 2,000 times 10. Okay, which is about that decimal. If I do 1 divided by 14.5, there it is. Okay, they are in fact the same thing. Okay, so degrees, let's see here. So that's going to be again, let me see, how do I want to do this? I'll give it as decimal. 0.0. 69. What is it? 2 over 29. When you simplify it exactly there. Okay. Degree per second. Okay. So, Steven, question?
So I did the first way in radians instead of degrees, but I got the same exact answer.
Okay.
Except not in the same units.
Interesting. Same exact answer, but not in the same. So you got like 1 over 14.5 or 0.069, but you did with radians instead of degrees. I feel like that shouldn't be the case because of the fact that degrees and radians, they wouldn't be equivalent like that. So I'm not sure. I'd have to look at that. I'd have to take a look at that. That's interesting. But
So like the inverse tangent of 5 has
uh-huh.
about 1.19. So I had it saved to theta, and then I took 1 over cosine theta squared, and I got 7.25.
Okay.
Exactly, and then I multiplied that by 2 and got 4.5 exactly.
Oh. All right. I'll have to take a look at that and see. I'll take a look and see. So, long story short here though, okay, there are different ways you can sometimes go about, there are sometimes different ways you can go about approaching these problems, okay? And it's really kind of like, what makes sense to you. We did ours in kind of like a piecemeal sense where we kind of like, did what we had there, rewrote it, and then, plugged in certain values that we still needed to find in other situations. Here, rewriting everything in terms of a single variable is helpful because then we only have the one variable to worry about, okay? It's a little bit more simplification and stuff like that too, but it's also, quite a different way to do it, and it's a little bit shorter there, maybe, okay? So, some options. Questions on either of these two ways? Questions?
How would you know, like my way, since you never had to do like the tangent or anything, how would you know if it's degrees or radians?
So, I see what you're saying now. You wouldn't know because you didn't have to use the actual stuff there. Right. Well, and so that goes back to Stephen's point there, where Stephen said that the radians, if he did it in terms of radians, and he still got the same solution. But I'm having trouble making sense of that because the rate of change, this is theta per time, and I feel like oh, okay. I think I have an idea. Because it's the change in it's the change in the angle. It won't matter whether you're in degrees or radians because we're talking about a change. So like the change will be the same proportionately if it's in terms of radians or if it's in degrees, I think. So yeah, it'll be probably like proportional kind of like measure.
2 over 29 degrees is an equivalent to 2 over 29 degrees.
No, I see what you're saying there, yes. But it's the fact that it's the change in the degrees per.
So would you just assume that it's degrees?
I see what you're saying.
The change in like 45 degrees to 90 degrees is the same as like pi fourths to pi halves.
Right, but we're exactly. So I think Let me get back to you on that though. But I think it has to do with like the change is proportional. But your question though, Carter, is like what? So should we put either one? Does it matter, right? Is that what your question is? And I think it would be okay to put either one there.
Okay.
And actually, long story short, I think it would be okay to put either one. It would be the same change. So yeah, I think it should be okay. Because again, we're talking about a rate of change of it, not the actual like measure or whatever kind of thing. So I think it would be okay because it would be proportional. Like Sarah was trying to argue there with like the change from 45 to 90, the same thing as pi over 4 to pi over 2.
Even though they're different angles.
Right, the
still
quantity
they're
and the
same.
change is the same. Yep,
Yeah.
exactly. So, okay,
3.
next problem, okay? So, but seriously though, I know we did spend a lot of time on that one, okay, and people tuned out because they're like, I don't really care, I got it one way, that's fine. So, but do we have any questions on either of these methods here? So, Sean?
So,
Because it is helpful to see it two different ways because potentially, you're good? Okay. Because potentially you guys will work on it in different methods as well. And so to see that you might be different than your neighbor, that's okay sometimes. Okay? Let's press on here though because we do have some more problems to do. Okay? So, a 25-foot ladder leans against the vertical wall. If the bottom of the ladder is slipping away from the base of the wall at the rate of 1 foot per second, how fast is the top of the ladder moving down the wall when the bottom of the ladder is 7 feet from the base? Okay? Pressing questions that you really have asked yourself when you've seen a ladder slipping down a vertical wall. So let's draw a picture here. All right, let's draw a picture. All right, so there's our vertical wall on the ground there. Okay, and we'll draw our 25-foot ladder. So this ladder here is 25 feet in length. Okay. So the bottom of the ladder is slipping away from the base of the wall at the rate of 1 foot per second. And so we're moving this way. And I'm going to call this at a rate. So we'll say that's an x, rate of change of x, right? Why x? Because it's kind of like a horizontal change in position, right? Horizontal change in position. So we'll use x to represent it because x, left and right and stuff like that. So we'll say dx dt is 1 foot per second there, moving that rate. It's sliding out, right? Okay. And we're also told we want the ladder to be 7 feet, when the bottom ladder is 7 feet from the base, I guess, of the wall there, right? So that means when x is 7 feet. Okay, so when the ladder is exactly 7 feet away from the wall there. Okay. So. How fast is the top of the ladder moving down the wall? So that's going to be how we represent that then. If I said dx dt for the rate of change of the ladder sliding away from the wall, what can we use then to represent the rate of change of the ladder moving down the wall? dy dt, right, for a vertical change there, exactly. So we're trying to find dy dt. Okay, that's what we're trying to find here. And of course, we could call the actual height of the ladder at whatever particular answer, we could call that y as well. Okay, that would be like the height. Okay, so how can we relate the variables in this situation? What can we use? So, Sean, you have a question? Question?
Does this have to be a 90-degree angle?
We were going to assume it's a 90-degree angle, that the wall makes a 90-degree angle, yes, there, with the ground. So, how can we relate these three pieces of information here? What can we use? Pythagorean Theorem. You are right. Okay, it's a right triangle. And we have a hypotenuse and the two legs here. So we'll say instead of a squared plus b squared, I'm going to go ahead and say x squared plus y squared equals, and then here's a choice, okay? You could say 25 if you wanted to there because the ladder's going to be 25. I'm going to put in c squared here just to kind of make a point though, okay? Just to make a point. Okay, but absolutely this is Pythagorean theorem. We have a right triangle, talking about the legs and the hypotenuse there. Okay. So now we've got our formula that relates everything. What should we do? Take the derivative, right, with respect to t. So what is the derivative of x squared with respect to t? 2x dx dt plus the derivative of y squared with respect to t, 2y dy dt equals, and then what about c squared? Well, it's going to be 0, but I just want to show you, you can also do it, think of it this way too. 0 is true, but I'll also show it this way to you too. Okay? So let me talk about the c right here. Okay? So I told you that you could put a 25 in here, well 25 squared I should say, sorry, because it is Pythagorean theorem, so it'll be 25 squared. Right? We could have put the 25 in here for the c, okay? And then taking the derivative of that, and if we took the derivative of 25 squared, what would this be? 0. But yet, I did not plug in the 25 just yet. I said, okay, let's just go ahead and just make this c squared. So instead, we'll take the derivative of it, 2c dc dt. Okay. Now, with this relationship, again, we'll get to the left-hand side in just a second. But the right-hand side here, what is c's value? 25, right? It's the length of the ladder. What would dc dt be here? 0, because is the ladder's length changing? No, it's not, okay? So dc dt is 0, which means this whole quantity would still end up being 0 anyway, okay? So it's going to end up being 0 because the ladder's length is not changing at all. So dc dt will end up being 0. The whole product there is 0. So it's going to be 0 anyway. Okay, it's going to be 0 anyway. And I'll write that as a note here, because the ladder's length doesn't change. So the rate of change of the ladder is 0. Okay? All right. What can we put in for x? 7. We've got that. What can we put in for dx dt? 1. Okay? Plus 2 times, what can we put in for y? Uh-oh, we have to solve for it. That's right. How can we solve for the y? Plug in your numbers, right? So we have 7 at the instant when the ladder is 7 feet away from the base of the wall. So I'll say 7 squared plus then the y squared there has got to equal 25 squared. So we're going to use the Pythagorean theorem here. Okay. So 25 squared minus 7 squared is going to give us 576. Okay. Oh. Okay, and so we get y equals 24. 25 squared, take away 7 squared, 576. And then square root of both sides. Right? Yeah. 25 squared is, 625, and then take away 7 squared. Okay, so we get y equals 24. So that's the height of the ladder as it's sliding down, because of course as the ladder's base is sliding out, the top of the ladder is going down. So, but now the height there is 24. And then dy dt, how fast is the top of the ladder moving down? We'll then have that right there. Okay, dy dt. Okay. And so then we solve from here, right? So we get 14. 2 times 24 is 48. Okay. And so we then get dy over dt equals negative 14 over 48, which simplifies a little bit, right, to negative 7 over 24. And that is going to be in what units? Feet per second. Okay? Does a negative rate of change make sense here? Why? Right, the y value, the height, is decreasing, so it makes sense to have a negative rate of change here. Okay? So you want to be careful about how you word this here. And it doesn't say, I mean, we got our answer there. It doesn't say to write a sentence, but if we were to write a sentence here, we want to be careful about this. What we do not want to say is, we do not want to say the ladder is moving down at a rate of negative 724 feet per second. I don't think this is a great way to write this sentence because you're saying it's moving down at a negative rate. It's like a double negative, so it really would make some people think like, like, okay. It's like saying like you're moving left with a velocity of negative 7 meters per second or something like that. Well, it's like, so is that a double negative and I'm really supposed to think it's moving to the right, or did you really mean it's moving left, comma, at the rate of negative 724 feet per second, So it's kind of like weird there. So ways you can get around that is you can just say the ladder is moving at a rate of negative 724 feet per second, and this is, you could then say like this is a downward motion or something like that. Okay. Okay. Something like that, but just be careful about saying what you mean. I think it's also okay to say the ladder is moving down at a rate of 724 feet per second. So you could just give me that alternatively and say the ladder is moving down at a rate of, then just pause at 724 feet per second. I think that gives a better indication of what you're supposed to be saying. Okay? But again, in here, you're not really asked for a sentence, so you can just circle your answer too. That's fine. Questions on any of that? Okay? Why don't you go ahead then and try number 8, draw a picture for this scenario. Okay? Just draw a picture. Just get the picture drawn. Okay? So ship A leaves from the same dock as ship B. Ship A is sailing south at the rate of 15 kilometers per hour, and after 1 hour, ship B starts sailing east at the rate of 40 kilometers per hour. How fast is the distance between the two ships changing 2 hours after ship A has left the dock? Okay, so go ahead and at least try and draw a picture here of this scenario. Try and draw a picture of this scenario. it looks like everyone's at least got a picture drawn, so that's good. And some of you guys have moved on because you want to just like get ahead, see if you can get it done. All right, so there is a little picture. All right, I drew my boat B kind of smaller. Whoops, it's hard to fit the B in there. Okay, so how can we relate? What's our scenario, or how can we relate these things together? What can we use? Pythagorean Theorem again. Exactly right. We have the distance here between these, but it's not the distance we're interested in, it's the rate of change of the distance. Okay, so we'll start with the a squared. Actually, I'm going to use x squared plus y squared again, because that's what I did with my rates. So x squared plus y squared equals c squared. Okay? If you use like a and b instead here, that's fine. I used x and y's. Okay, so it's really up to you which one you want to use there, but just be careful. My x goes with the b, the y goes with the a there. Okay, so there's a relationship, and so we'll go ahead and then take the derivative here. So the derivative of 2x with respect to time, 2x dx dt, right? We don't need to spend too much time on that because we've seen it. 2y dy dt was just in the previous problem, and then 2c dc dt here. Okay. Okay, and let's see here. I have for B, the ship B here, I called that dx dt. So for the dx dt here, I know that that's going to be 40. For the dy dt, I called that the rate of change of A. It's moving away from the dock at a rate of 15 kilometers per hour. So we'll say that's 15 there. And then dc dt is what we're solving for. Okay, so we have 3 different values we still got to come up with that were not given to us in the problem, right? So dx dt, the rate of change, the ship is sailing east at a rate, so that's the rate of change there, 40 kilometers per hour. The ship A is sailing south at a rate of 15 kilometers per hour, so again, that's a rate of change there, the derivative. But we still need to come up with an x, a y, and a c because, and dc dt is what we're trying to solve for, the rate of change of the distance between these two. Here the rate of change is, and this is changing the distance between the two, not like the latter problem where it was always going to be 25. So we got to come up with an x, we got to come up with a y, we got to come up with a c. So let's focus maybe on this x first. So for x, I got to figure out ship B. Actually, it might be easier to figure out ship A's distance first. Let's figure out ship A's distance first. I think that's easier. Okay, so ship A is sailing south at the rate of 15 kilometers per hour. So how far away is what's this distance here that ship A is away from the dock? 30. How do you know? It's traveling 2 hours at 15 kilometers per hour at constant speed, so it's going to be 30 kilometers away. Okay, and so our y, that's y for me. You guys may have had it be b or whatever kind of thing, but for my y, or for a, I guess you might have called it your a length. That's gonna be 30, right? Okay. What about our x? What's that? How far away is that ship B? 40, right? Okay. So after 1 hour, ship B starts sailing east. So ship A has sailed for an hour, ship B then starts sailing east. So from 2 hours after ship A left the dock, right, if ship A has been traveling for 2 hours, how long has ship B been traveling for? What length of time? If ship A was sailing for 2 hours, ship B left an hour later, then how long has ship B been sailing? Not 2 hours. Just 1 hour, right? If ship A was sailing for 2 hours and then ship B started an hour when after ship A started, it's only been sailing for 1 hour since ship A has started. Okay? So 1 times the 40 there gives us 40, and that's that length right there. Okay, 40 kilometers. So then that's going to be 40 in for x there. Okay, and then, well, what about the length c then? Pythagorean Theorem. That's 30, that's 40. So, well, what's the hypotenuse going to be? 50, right? 3, 4, 5 triangle. So 30 squared plus 40 squared equals c squared. And so we get, oh goodness, I think that'll be 2,500 there, I think, yeah. So c equals 50. Okay, so yep, so C is 50. All right. So that was quite a bit. So questions on any of those values there? Did anyone get lost? Anyone want to just refresh their memory about where anything came from here? Questions on any of that? All right. So then we solve here. Okay. So 1600 times 2 will be 3200. And then let's see here. Well, that's going to be 30 times 30 will be 9,000. Or 900. Sorry, 900. Can't do math, right? 40 times 2. Yeah, 3,200. 2 times 30 times 15. There you go. 900 equals 100 dc over dt. Okay, and so that's going to add up to give us 4,100 equals 100 dc dt. And so we get then that we get 41. Okay, or in other words, 41 kilometers per hour. Okay, 41 kilometers per hour there. Questions on any of that? Okay. All right. So I want to make sure we're doing all right here. I think we're doing okay. Okay. Why don't you guys go ahead and try number 9. This one's very similar to that last one we did. So I think I'm going to let you guys try this one here on your own. Okay. So it's very similar. I would say maybe even a little bit easier. Okay, than the last one. So go ahead and try number 9 real quick. Okay. See what you can come up with there. It's a very similar situation. So see what you can come up with there.
two.
It's,
I was talking about
it should
number
be,
one.
you put the rate in, it should be 120 in there. Good. No, I was saying. I'm not gonna worry about that one right now because we'll look at that. Good. Good. So good job.
Was the,
So
It's on volume equals
how do you get 5, 6 there? So is that your dx dt? So the rate of change here is this. Yeah, exactly, because it's going away at that rate. This one then would be 60, so that's your dy dt there, okay? Rate of change.
Okay, in the interest of time here, because I do want to get to this last question, so I'll go ahead and give you, there's number 9, okay? 65 miles per hour is going to be your solution there. Okay? It's going to be your solution there. All right? The cars are moving apart at a rate of 65 miles per hour. Okay? All right. Last one here, take a look at number 10, a cylindrical tank. Cylindrical tank. Okay, like that. Of radius 10 feet, and I guess I'll maybe do. Okay, so radius is 10 feet. Okay, is being filled with wheat at the rate of 314 cubic feet per minute. Okay, how fast is the depth of the wheat increasing? What am I saying? Weird. All right. So anyway, what is a formula that we can use to relate? Oh, sorry. Let me identify this. So this value here, 314 cubic feet per minute, that is a what? dV dt. So dV over dt. We got wheat kind of pouring in here. 314 feet cubed per minute. Okay. What is the formula here that we want to use to relate these pieces of information? Volume of a cylinder. Again, volume of a cylinder is just pi r squared h.
Do you really have this memorized?
Yeah. It's the same as, it's just like circle pi r squared times the height to make it as a cylinder.
All the volumes memorized?
You don't have to. No, I
No,
mean,
but
I don't
you
have
do.
all of them memorized, no, but I have the important ones, like this one, you know. So anyway, okay. Yeah, exactly. It's just this, and it'll make more sense actually when we talk about integration later. But anyway,
What is the example?
we got to finish this up here real quick. So at this point, okay, what should we do? We don't have a relationship. We don't have a relationship between r and h here, so we got to take the derivative as it's written. So dv over dt equals, got to use the product rule here, so it's going to be the second times the derivative of the first, so 2 pi r dr dt plus the first pi r squared times the derivative of the second dh dt. Now there's a hint here, right? What is dr dt for a cylinder? 0, right? The cylinder is always going to have this constant radius. So this whole thing goes away because dr dt equals 0. Okay? And so we end up with just what the dv dt equals, oh, that's a pi. That's why I was like, what did I write there? Pi r squared times dh dt. And then you can substitute in the appropriate piece of information. How fast is the depth of wheat changing? That's what you're solving for is dh dt. So you have r is 10. You have dv dt. It's 314. Okay? And then you solve from there. Okay? And you'll get like 1. Yeah. you get like 1.
Or you can get 3.
Or we could just get
Approximately.
314 over 1 and something like that. Because we can.
Which will be, of course, 1 foot per minute. No, but because of rounding, it will be 1. Okay. Wow, I really apologize, guys. We took the entire class, okay? I try not to do too many of those. Yeah, let's blame Carter. No, I'm just kidding. It's not Carter's fault. It is not Carter's fault. I could have just as easily said, Carter, let's not. So I'm okay. I'm glad we did that.